them as they come.
And,
Okay.
well, they're welcome. If I put something up there they don't understand,
Okay.
we need to address that right then.
Got it.
All right, so, yeah, I'm sorry.
Good afternoon, ladies and gentlemen. Thanks for coming. Thanks especially to those folks that moved up front at my request. I appreciate it a lot. We're going to get started. We're here to talk today about sustainable development operations. I hope that's of interest to you. Should be. It's for credits. And if you want credits, like every other session, this table at the end of the session, I have signature sheets that you need to sign so that the New York Society of Professional Engineers doesn't yell at me and verifies that you were actually here. So thanks a lot. Garen's laughing because he knows how that works. You know, New York-GEO has been doing this, I think, since 2014. That is having a conference. And I'm guessing that there's a reason Garen keeps getting invited back time after time. It's because he's totally experienced. He is done a lot of things both nationally and internationally. He's an innovator, a designer, a patenter, a contributor. He's a founding member of the Gray Edge Group, a private entrepreneur. There isn't anything that I could tell that you haven't done, and he's willing to share it with us. So there's a reason he's here, and we really, really appreciate it. Come to find out, we were almost neighbors during my time in Texas, those 25 years. I probably drove by your house up in Oklahoma 3 or 4 times, and I would have if I know, that's for sure, and I could have used one at times. So he's going to talk to us today. I'm going to turn it over to him. At the end, come over and after question and answers and sign up for PDH credits. But right now, give a warm welcome to Garen Ewbank.
Thank you, John. Good job. Well, now if I could just live up to that, we'll be okay. First of all, are there any people here that are financiers? Financial people? Well, that's a damn problem. Okay. No. I mean, like, put funding into these projects. Or come to you and say, hey, if you build it, I'll fund it. Why do you think that is? They're not at our conference. Why? Anybody have any thoughts? Well, let me give you an example. There was a big project in Tulsa, Oklahoma. An oil and gas guy made a lot of money, and he decided to build a big park. And they put a number of buildings out there, I mean big venue buildings, and they wanted to be green, so they went ground source. Okay, the electric utility in that area decided, man, that's a great deal. So this group went to the utility and said, will you give us some incentive money to do this? And of course, they kept trying to ratchet it up and more and more and more. So they said, yeah, okay. And before they started building this project, the electric company asked me to come over and review what was going to happen. So I did. They had this big meeting, and the utility said, what do you think, Garen? I didn't want to say it, but I said, well, these loops are all going to get hot in about 8 years. Okay. 11 years later, this group came back to the utility and said, well, our loops got hot at about 8 years. The lady from the utility played the conversation from 11 years earlier where we'd had that meeting to them. And I'm going to go through some things here today that'll help us understand how to stay out of that and understand what thermal drift is all about and how we can control it. And so if I get lost, Don, raise your hand. Okay. Any questions you can have, you can ask Don. Okay. Oh, yeah. Okay. All right. So, I've covered that we got to do something about financing. The reason people don't like to finance these things because they can't forecast the outcomes. All right? Okay. And, after about 5 years, most of the engineers have already walked. And so there's not a whole lot of recourse there. Okay. So are you being professional when your systems overheat? Well, the first thing you want to blame is the ground. Isn't it? Yeah. Okay. So we're going to talk a little bit about how to get around that, how to manage that, and how to move forward with it. And actually, it's pretty simple. You're going to see some equations in here. Don't get bugged out about them. They're very simple equations. I'm using them to explain my thought process, okay? And my thought process sometimes is bumpy, okay? So you'll see this as we go through here. So anyway, that's who I am, Garen Ewbank. So I'm going to talk about thermal risk, as in risk, performance, or financial compression in these water loops, ambient temperature loops, district systems, 2 pipes, 4 pipes, whatever you want to talk about. But I'm going to talk about how we can compress that risk on the performance side. And then I'm going to go talk about how we compress that risk on the financial side so we can get some of those financial people to come in and help us with these big projects, all right? In this building, there is a bunch of financial people having a big meeting today and yesterday. And so I asked one of them, okay, well, he'd heard about ground source, but he's not sure it works. That's what he said, okay? I'm going like, okay. So we're going to work as a team, a unit, NY-GEO, IGSPA, Association of Energy Engineers, to kind of take and de-risk all this stuff so that the financial guy at the end of it has something he can rely on. And that's pretty easy to do, actually, all right? It's just a bunch more steps than we've been doing in the past. So here we go, ready? All right. So if we look at these things, some of our objectives I want you to be able to come through with: risk management of the operations, design, and financing of thermal energy systems known as TENS, thermal energy networks. I've gone beyond that now. I have a deal when we get through all this, we'll call it thermal infrastructure networks, okay? TINs, T-I-Ns, okay? And if you have a T-I-N, we know that we have a reliable financial model that's out there, and it will hit those goals, all right? First, we're going to identify the structural mathematical components of these TINs. There's a lot of different things connected to it, and we've got to figure that out and get it right. Then we're going to connect the math and the design, and that is going to connect to the financials, all right? At each step, I want to mitigate the risk at each branch of the design, operations, control, and the financing, all right? So I know that we've all been through these steps, and we usually end up with some sort of life cycle cost or first cost or payback period or something like that on a system that's going to last 50 to 100 years, all right? When we do big power plants, big water plants, big sewer plants, all those systems, you don't hear about what's the payback, do you? Okay. We're going to go into that arena and category, guys, the way we do that, okay? And so we have some methods. We're going to lower the first cost and improve operations and efficiencies. I know that sounds like it might be hard to do, but one of my partners, Don knows him really well, did a university, And as they added new buildings, went from 2,500 students to 13,500 students, the capital expenditures for the new buildings to go ground source were reduced by 62%. In other words, they used the diversity of the campus, didn't have to add more ground heat exchangers, all right? And you can do that, guys, all right? There's just some modeling you have to go through to get there, okay? My background, I'm an industrial engineer. I grew up drilling water wells and oil and gas wells across Oklahoma. So that's what I did. I built rigs for a long time. And during the 80s, when nobody wanted a water well, I tried to figure out a way to get my water well rig owners some work. And I got into this business and fell in love because it's all about efficiency. I'm an industrial engineer. So there we go. That made sense to me. And that's where I went with this, all right? Okay. We must scale geothermal without scaling the risk. I don't want your loops or your ground heat exchanger or whatever you got getting hot in 10 years, 8 years, 7 years. Usually it shows up in about 7 years, okay? The subsurface uncertainty drives the internal rate of return variability, okay? Loop drift over time drives the long-term EUI degradation, okay? Gets less efficient, all right? Stays up to either up or down at the temperature bands, okay? So I've got to compress the thermal risk to be able to manage these things properly as we go forward. Yes, we can do that, okay. Press that back a little bit, okay. So the EUI is the controllable variable that we're going to be looking at in all these systems as we go forward. Thermal systems dominate, the building energy. How are we going to do this? Where are we going to put it? But we also need to think about part load performance, and that defines the annual EUI. You know about part loads? You heard about variable refrigerant flow systems? They're the cat's meow, aren't they? Yeah, everybody's buying them, everybody's selling them. They're part load machines. That's really all they are. And they have their own rating system called the Integrated Energy Efficiency Ratio, IEER, all right? So they got their own way to classify themselves and everything, but really it's just about part loads. And we find that there's a rule called the 50-90 rule, and what it says is, on a building, on a group of buildings, about 90% of the time, those buildings will be at 50% or less of the load. And that's true, okay? All the systems I've looked at, we've documented, it's there, okay? It does work. So we have to handle that last 10%, and we can either do it by building a ground heat exchanger for the full combined total loads at peak, or we can use the 50-90 rule and bring in some supplemental systems. And a lot of times for that very short duration, short period, those supplemental items, which could be existing cooling towers and boilers in a group of buildings, you can bring those on and start conditioning your loop through the loop of the building to your water loop. Hey, makes sense, okay? And so that's the first step in how we can reduce costs. The second step can be, if I have a loop that doesn't go back to central plant, like an ambient temperature loop, just a big loop, just circulates water. It has central pumping, not a central plant. All the sinks and sources and all the loads are connected by a parallel connection, okay, to that one pipe loop. When I do that, I can capture all of the diversity within that ambient temperature loop. Once I start doing that, sometimes I don't even have to heat and cool anything. The buildings run, they take care of the temperatures, everything will be fine. And we find that happens pretty often, okay? We've got one, about 4,200 tons system that is using 8 horsepower to pump the entire ambient temperature loop. Okay, that's pretty amazing, isn't it? All right. Yeah, it can be done. All right. So we can talk about those things a little bit later. Oh, where are we at? There's 50/90 rule. Okay. So when we get into the heat transfer in the earth, jump down that last line. It makes more sense for everybody. Okay. But the top line is how I arrived at the bottom one, just so you understand it. So we know that the conductivity determines the magnitude, the peaks. All right? So that'll be the maximum and minimum entering water temperature in that loop as we operate it. The volumetric heat capacity, or the density times specific heat, average of the earth that we're connected to, defines the storage that's in that system. Now we're getting ready to go to capacity. All right. So the thermal diffusivity, alpha, is a heat transfer in the Earth's time behavior. And you can see where I'm going now because I'm getting ready to guide that thermal drift over time. And it can be done very easily. Okay. So as we dig into this thing, we know that the diffusivity is a ratio of the conductivity to the volumetric heat capacity. And we know that conductivity governs the magnitude, but the volumetric heat capacity governs the temperature drift over time. And that's where it really becomes important. That's where you get away from having to worry about something that's going to get hot in 8 or 10 years or something like that. All right. Am I making sense so far? Okay, good. I got some nods, yes, and I got some people that looked at the ceiling. Okay, well, that's fine, okay. Once we understand that the conductivity is the magnitude, how far, the volumetric heat capacity is that drift, now we can start designing in those systems, but guess what you got to be able to do? Quantify it. Has anybody here quantified volumetric heat capacity? What? Yeah. I do have a machine that does that. All right. Okay. And really it's done, ASHRAE has 3 test standards that we use: line source, cylindrical, and then the numerical modeling. And we do all 3 of those in that data set. So once we get there, yes, we can directly tell you what that volumetric heat capacity on that Earth locally is going to be. With that, then, we can now start managing the thermal drift with time, okay? And what's important is, let's look at, one estimate and one measured. It's really important because I did one in Colorado where the old style, we would take the drilling log and we would estimate diffusivity from the rock properties, the soil properties, and average them, okay? And I've done about, 3,000 or 4,000 tests, and I thought I was pretty good at it. I come up with a 0.98 diffusivity feet squared per day. The measured diffusivity was 1.9. Okay, guys, that's a big difference. Okay, I'm just telling you. So we can go ahead and build giant systems, spend a damn lot of money that nobody's going to finance, or we can figure this stuff out. Okay, and we're going to figure it out. If you do that, you can also reduce the loop lengths and the capital cost. Now we're getting something in that gets the finance people's attention. All right. We're not managing their risk yet, but we're lowering it. They like to hear that, right? Okay. And this is value engineering on steroids. It's not shortening the loops because it makes it cheaper. It's because we're making it correct. And there's a big difference. All right. Okay. So as we go through this, I'm gonna go back through and I'm gonna repeat this a number of times, but thermal conductivity, okay, identifies what? The peaks. Volumetric heat capacity does what? Manage the drift of the system over time. So when you have a borehole or you have a whole ground heat exchanger down there, and it's a vertical mostly, all right, you do a normal thermal response test and you look at the radial heat flow going out. That's all you're looking at. But these systems have space and they have time. So I got a borehole. It has a cylinder around it that's changing in temperature as it goes further out. It goes out radially, so it gets bigger. And so now I've got a space and time constraint that I have to think about radially. Also, I have the same thing going on vertically. Okay, so from the deeper earth temperature, geothermal gradient, all the way to what it's doing at surface, we have to know that also. So now we're getting our hands around what we have to have for these really large systems to be designed to be successful. All right, and I'm after that drift prediction. That's where I'm going. Okay. So, okay, we're gonna get through this, but what we do with what I call the advanced thermal response testing is it does measure the conductivity and far field, but it further measures the volumetric heat capacity. And to do that, I have to calibrate a digital twin and model it. And what this allows me then to do is reduce the uncertainty on the values and the operations of these systems. Now that's kind of new, okay? Took me a long time to figure this out, guys. I'm 77, okay? I did, okay? This is not something I come up with immediately, because, you know, I was back in the old days, you know, one building, giant heat exchanger, knock yourself out, blah, blah, blah. We had a lot of incentives. We used to have residentially a lot of tax incentives federally. That's gone away, but we have it commercially, and this is gonna roll right into the commercial development of these systems. All right. So, I wanna reduce the uncertainty of that subsurface. Let's look at the impact that we can get out of sizing if we understand and stay within those probability ranges. Zeneb, it's stochastic, okay? Okay. And on one project, we would have been at 300 to 350 feet per ton. When we measure things right, we go from about 200, 250 feet per ton. And that's site dependent, you know, for those numbers. That's not a rule of thumb. Don't write that down, okay? But I did reduce the capital expenditures, and I managed the internal rate of return variability. All right. And you see that I'm headed to the finance guys now, right? Okay. The 30-year drift concept is really important because if I measure the volumetric heat capacity, rho C, I can narrow that band big time. If I assume it, I gotta have a big band, all right? And so measurement and quantification compresses thermal risk. And that's what I was after. I hope that makes sense, okay? So an ambient temperature loop, which is simply a big one pipe that circulates, has central pumping and not a central plant. All the loads and all the sinks and sources are parallel connections, close coupled connections, to that one pipe, all right? With that, it allows us to put a thermal gateway in there, and now I know what each node is doing in real time. And I call those thermal gateways. Next temp, we do that, okay? We can use that one big pipe for thermal transport in real time. A building that's cooling may supply heat for a building that needs heating, all right? We could probably do a data center take all that heat and put it in a thermal loop and heat the citizens, couldn't we? Yeah. And we need to quit throwing away that energy, guys. All right? I'm about efficiency. I'm not necessarily a tree hugger, but I will hug a tree, especially if it has apples on it. All right? But anyway, we're after that diversity capture. All right. So now if we're going to go to this next step, these are the processes that are required to get to where I want to go. And I'll explain some of these terms. They're new. All right. The advanced thermal response test is precision measurement with a digital twin that captures the volumetric heat capacity. The ground heat exchanger now becomes seasonal storage, not the primary source sink for peaks. All right. The ambient temperature loop is a transport spine. It's just pumping water around. And like I said, that 4,200 tons on that one university, we're pumping that loop with 8 horsepower. Okay. So you can take 4,200 ton times 3, that's the gallons per minute. We're doing that with 8 horsepower. Yeah, that's pretty amazing. Okay. And because we're operating off a temperature differential, not a pressure differential. All right. Next, we go into the polymodal mode, and those are the efficiency governors that connect to these systems. It can be something like a air to water unit heat pump that gives me, from the outside air, hot water, outside air gives me cold water. I can temperature the loop with that. And for that last 10% of the year, I don't have to run it very much. But it does have capital expenditure. And if it's cheaper than an additional ground heat exchanger, it makes sense. Okay. It can be a polymodal heat pump, one that does air source cooling, water source cooling, and moves the heat bidirectionally between the outside air and the water loop. I have a patent on that process. All right. So I've kind of went down this line as I've thought through all this, and I have a goal in where I'm going. All right. So that's where we're headed. But that efficiency governor is really important because it helps me manage the thermal drift. All right. Along with the math. All right. So, don't worry too much about this, but that's what it does. But I'm trying to maintain a stable COP on my machines. And to do that, I have to have what? They like happy water temperature, don't they? Yeah, and that's what we're driving to. Keep it in that 40 to 85 degree range. You may want to extend it depending where we're at in latitude. Okay. You may get lower, you may get higher, but we want to keep it in a range where those heat pumps are happy in their operation and the most efficient. And we can do that. All right. There's another, and Oak Ridge has done a little bit of this, Oak Ridge National Labs, excuse me. And if I use acronyms or whatever that everybody doesn't understand, throw your hand up, because I tend to do that, okay? So what's in my head comes out of my mouth, so we'll just go from that. Okay, so as we go through these, we've got to understand that the priorities are optimal source sink to meet the multiple loads. I want to reduce peak electric demand, which we can do. We have one system where the winter COP is 8.9. Now, if you have one that's close to that, raise your hand. 4 isn't close. Okay, yeah, you can have a 5. Yeah. All right. Why? It's because of diversity in the system. Okay. And so when you look at that thing, I want the EUI on the system, not on the box and not on the building. The buildings, we got to take care of themselves. Okay. And the commissioning and stuff that were talked about earlier is really important. Make sure it's there, make sure it's put in and operates correctly. Then we want to reduce the drift in that thermal loop. I want to make sure it doesn't get out of those bounds. And all systems, guys, let's take a heat pump that has a COP of 4, okay? So when it's heating, it takes 3 from the earth, adds 1 from the utility, and puts 4 into the space. Now, that same air handling unit, when I go to cooling, turns around, it takes 4 from the space, adds 1 from the utility, and puts 5 in the ground. So now my ground loop is already 5 over 3. I'm unbalanced. But the load was balanced. It's 4 and 4. All right? So once we understand that, now we can start seeing through this whole process, and our management of those assistive devices becomes a lot easier. All right? And it's time dependent. Okay. So what is system development operations? Where I came on this, I was developing the advanced thermal response test, and I got to thinking, I need to be able to manage large systems. Something like, 100,000 tons, a city, a town, a giant campus, something like that. Because if we're gonna make a change, then let's really make a change, okay? Let's quit pussyfooting around, and we're not gonna get it done unless the capital structure comes to our industry. It is not there now. Everything has to be a pilot project or something like that to prove up these things work. Earth's been here a long time, okay? It works, okay? Trust me, it does, okay? So what we're gonna do is in SDOps, which is originally built and modeled to take the IT industry and have it meet up with what the plant was doing, all right? So I've got production processes going through, raw materials, finished goods over here, and the IT is supposed to measure all this stuff and report it. They never talk to each other, ever. So a group of people did what they called sustainable development operations to marry up those groups. When I saw that, I'm going like, that's exactly what we're doing. It is, all right? So I read the book about SDOps, and I have a little IT background, so I could understand most of it, okay? But once I got the facts and the connectors, it really hit me, and it really hit me when I read a book called The Phoenix Project. If you'll read that book, you'll understand where I'm coming from, all right? Once we got that, then I knew what I was gonna be doing, all right? That's where this whole DevOps deal came from, all right? So now we have a plant that's called a ground heat exchanger. It's called a boiler, a chiller, cooling tower, whatever. Those are all machines in the plant to produce the outcome, which is space comfort, right? Or hot water, or something like that. It's just a process. It's a production process. We go through it and we do it all the time, all right? So we need to measure, then model, then detect, correct, and institutionalize our processes. And that becomes straightforward if you follow the SDOps guidelines and rules on how to do this. So we get into a continuous governance of the thermal infrastructure. That's the result I'm looking for, all right? How do I handle it? How do I manage it? In 30 years, will it still be operating properly? Unlike that one in Tulsa, Oklahoma, 8 years later, the loops got hot. Okay? So everybody that's in finance has heard the loops got hot in 8 years story, haven't they? Every one of them, yep. They're going, okay. Well, guys, we have ways around that. We can directly de-risk both the performance side for the water loop and de-risk the financial side for the money people. And that's a good deal. We have not been able to do that before. We're always going over to payback, blah, 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 all these metrics that don't apply to the systems that we're building. Don, how long has some of your systems been operating? 30 years. Yeah, I've got some 30 years. Anybody have anything before 1976? Me, okay. You do? Thermals, oh, you just, no, okay. Look at that look on her face. I saw your hand move. Okay, all right. Well, yeah, I'm looking for some participation here. Okay. But we can do this, and the continuous structure is how you acquire the data and parse it and use it. That's really all it is. Not complicated, but it's a whole new way of doing things that we've not done before. And when we do it right, the financial people go, I'm in. Then you can get that long-term capital. You can get something like the electric utilities get for their generating plants, or the gas distribution systems get for their pipe in the ground, okay? Those are long-term deals, and they're return on what you put in capital in the asset, all right? They get paid back by some sort of volumetric pricing, either in KW or MCF or something like that. But we have a very similar structure that we can do that, and we know how many gallons we're moving in the temperature differential. M.C sub P, anybody, you okay? Yeah. Delta T, yeah. Yeah, we can do that. The flow, yeah, times GPM, times the differential temperature. Boom. That's the BTUs. And I'm going to tell you now, I like to think in those in terms of KW or W, not BTUs. All right, that's just me, but anyway. All right, going on. That continuous commissioning framework is going to require 8760 monitoring. I got to look at it in real time. Where's this thing going? What's it doing? This allows us to do a portfolio tracking where I may have a number of loops that are all interconnected, all right? The Lego build out of these systems. They just keep growing together. With that, then I can do that drift detection, and I can get the key performance indicators for that whole system. It's pretty straightforward, okay? So now we're moving water loops into being similar to the grid assets, okay? Distributed thermal storage, peak demand stabilization, grid responsive polymodal operations. I want to keep out of that scary zone that costs a lot of money. I hope that makes sense. All right, good, okay. By the way, what we're talking about will align with your climate goals. And where are they at right now? What does Hochul say? You gonna suspend them? Is you gonna drive them harder for New York? CLCPA? Anybody know? They're gonna slide it off. Lots of delay, you're right, John. Yeah, and have they said how long the delay is yet? Too long. Yeah, okay. Which means that they didn't have a way really to manage what they were trying to do, okay? It's hard to change a whole lot of clients' use of energy without giving them an easy pathway to do that. And that's what we're trying to do. So it matters. Utilities, they become able to do a dispatchable thermal load. Developers can reduce the capital expenditures variability. If you ever built a big project, it can get quite variable, okay? Investors get tighter internal rate of return metrics and bands. They know where they're going to end up, all right? And the owner has a continuous EUI reduction over a long period of time. That's pretty handsome, isn't it? Yeah, I kind of like that. All right, so we have some questions. One is, how do we scale geothermal without scaling risk? This is the Brooklyn question, the New York-GEO question, the Massachusetts question, and other states. I'm punching Zaneb back there. All right. How do we do it? We got to be able to drive the thermal drift in these systems. Once we can manage that, we got our hands around this whole thing. How do we electrify without oversizing? I know those VRF systems are really good, but when it gets really hot or really cold, they're simply a refrigerant system, okay? And so they're gonna start busting peak. And if you don't believe that, try to overspeed them, which some people do, okay? They'll bring in a 50 hertz machine, and then when they get ready for a peaking event, they take her up to 60 hertz. There's some manufacturers that actually do that, okay? And there's some people that do that, okay? But when we do that, the demand on the system goes sky high. It's not linear, okay? It has a little bit of kick to the curve at the end, all right? So how do we integrate the thermal and power grids? Let's just replicate what the power industry's done, and we're gonna do the same thing. It's pretty simple, all right? I'll give you a gallon of water and you can either take heat from it or, put heat in it. I don't care, but I'll pump it for you. I'll make it available and I'll do that exchange. Now, I may take that little heat you gave me and give it to the neighbor down the road, but that balances the system and makes it more sustainable for everybody. So the best averaging for the ownership, the users, is exactly that diversity component. That is enormous, and we've never quantified that in the past. We're going to in the future, all right? I may have to live to be 100, I'm not knowing that I want to do that, but that's where we got to go, all right? And so I'm looking at all of you out here, and I'm saying, help us on this process, understand why it's so important, and let's get to work. And next time we're here, I want to have Merrill Lynch, all those guys in here saying, Don, I want to do your next project. I'll finance it for you, okay? Wherever it's at. Gino, same thing. Up in Canada, here we go. We're ready. Now you have people that will do some financing, but it's a little bit onerous, and they tend to want to eliminate the risk by what? Adding more loop, adding capital expenditures, okay? And so if they're sitting there at, 10% they're charging you, and I put another 20% in the cost basis, guess what they get? More return, because all they're supplying is money, probably not their own, okay? So we can get there, guys. It's something that we can do. Do you have any questions from the audience?
Let me get up there with the microphone.
Okay, come on, John.
And people will let us know who they are and what organization they're from.
Please.
Garen, when John Chivacco hears this, you're coming back next time, I'm almost guarantee it.
He won't listen to it.
Hi, Garen. Thank you so much for your presentation. My name's Josh Chung, and I'm from Frontier Energy out in Cazenovia, New York. And as a former graduate of SUNY ESF, I did a little bit of financial analyses on geothermal and solar plants and wind turbines. Mm-hmm. My question is for you on I guess, not the networking side. How do you plan on getting those guys into your conference, into a conference like this? How do you plan on getting them here?
By being successful.
Yeah.
Yeah, that's the only way it'll work.
Okay.
They got to see it's going to work, and we do a lot of rescue work, okay? Ground heat exchanger, the overheat, come and help us, blah, blah, blah. And they're always pointing to the ground heat exchanger, and I know that forward and backwards. I can tell real quick. Mm-hmm. Right? An example, we had a 600-bed hospital that the ground heat exchanger was up to 105 degrees. They were panicking. And they had equipment, 30-some rooftop units that had been built out as air source units, converted to water source units with reheat coils. Mm-hmm. The fan was right up against the reheat coils, so we had very bad airflow through them. Okay, we got to stop doing stuff like that.
Yeah.
Okay, if we're successful, okay, and don't do these little deals that just, oh, if we're successful, thank you, we won't have those hiccups. All right? And a good design engineer, I'm telling you, you guys know what you're doing. You need a little help. We're here to give it. There's ways you can do it. Real easy, but this is new. But SDOps in the IT and the production world is no different than what we're doing. It's exactly a very similar process. The other thing is financially, we also do the modeling. If I'm managing the drift, now I can manage the outputs. Now I can manage what the rates are gonna be, okay? And we can go through that and look at some model predictive control systems that rely on Monte Carlo modeling and some other stuff to get these outputs so we know where we're gonna be. It's easy to do. In fact, financial people do it every day on their deals, okay? So it's nothing new. Yeah.
Thank you so much.
Yeah, thank you for the question.
Great question.
Hello, my name is Alicia Jenkins, Sierra Club, Connecticut, the girl with the face.
And yeah,
I made another face because I just thought about what you, well, thank you for your speech and your slides and your work. I thought about the fact that AI exists and there's trillions of dollars invested in that and they haven't seen any return on their investments, and yet they're scared of this. So I'm just wondering, how can we use that language that they use for AI and shift it over to here where with something that actually works?
Well, you can, okay? And I did use AI to help me. The math's fine with me. It's the words that I gotta get simplistic when I do these deals, okay? And so I use AI to help me get the words right. Keep shortening it, get it right, keep shortening it, get it right. I got a book in there, it's 115 pages long, and when I fully expand it, it'll be about 600 pages with the proper prose in it. And I'll have to have AI help me do that, because this brain won't last that long, okay? After about a week of it, you get rum done. But you're right. The next phases we're gonna do is, we really need to take that whole process to the people. And we're not doing it now. We're just saying, pay your power bill, aren't we? Yeah. Well, if you have changing weather, it's sometimes hard to pay your power bill, okay? And I don't care if that's on a daily deal or on a 10-year scheme, we have to be prepared to handle that for them. So there we go. Anybody else? Nope.
Dan Cowan from Finite. Talking about your ambient temperature loop and different people on it across the loop and you being at a constant delta T pumping versus a pressure pumping, the person at the end of the loop, right, is always going to be suffering the worst kind of entering water temperatures.
No.
So I see you shaking your head no. So can you explain to me, like, when we go cooling dominant in the summer?
If you're all alike, all the facilities are the same in usage, you're correct. So a giant residential system, I know a company that's going to Colorado, hooking up with a builder, and they're gonna try to put in a district system, all right? All those homes are alike. At best, they'll have 19% diversity, okay? If I can get into a community where I have, and that's Borough Happel, okay? They did a great job on that. We were lucky enough to go to an RMI Spark deal, what, 5 years ago? How long ago was that? Something like that? All right. And they had produced that chart for us. As we get closer to New York City, the diversity is about 50-50.
And I can understand that in like a heating mode, right?
No, in cooling mode too.
Really?
Yeah,
Okay.
yeah. It's not something that falls out until you've measured it and done it, okay? But if you're all alike, it's not gonna work, okay? So don't go into a big project all the same buildings, that's what I'm saying.
Good questions.
Yeah.
Any more? I was hoping you'd raise your hand.
Oh, I'm going to be mad at her.
Get ready.
Oh, by the way,
Oh.
this gal has done yeoman's work in getting us this whole industry off the ground and moving. Now your question.
Yeah, now I have to crawl under the table or something. All right. Thanks, Garen. And I really appreciated you taking all of the puzzles from the physics to the economics puzzle pieces and putting them together. I think when I'm talking to folks who are looking at the investment mindset, the kind of preventative containment of risk that you're proposing with the improved measurement and prediction makes tons of sense. And there's a whole bunch of other variability, including, for example, when you're at utility scale, you have utility management, but you also have the ability for customers to come on and off. Mm-hmm. And also we have a changing climate and other factors. Perhaps there's a drought and the ground goes dry, et cetera. So the reality of kind of a dynamic system is that continuous monitoring, I think one of the things that is I'm curious about in your outline is that the time to adjust, if you're monitoring, the time that is needed to adjust your system to respond to new circumstances is quite large.
Oh, yeah.
And that has been one of the biggest risk reductions to an investor's mindset, that even if something changes, even if you got it perfect, or you have years to respond to a drift. And I just where does that fit into your proposal?
Yeah, generally on managing the drift, we need about 30 days. Okay, so we'll see it going, and 30 days later, we'll be back within the envelopes. We'll never exceed the envelopes. But I have to look ahead about 30 days on where this thing's at. And I know that by the temperature of the loop, okay? Am I approaching either the maximum or the minimum? Okay. There are certain probabilistic bands that I have to look at. Once I see those, I say, I need a cooling tower. I need a boiler. I need something.
But 30 days to see it and diagnose it.
You see it, and then you start managing immediately.
Right.
Because you're approaching either the upper or lower limits. It takes about 30 days to get everything totally back in line, because I got to command equipment.
So that's the kind of thermal management utility. But they already have to have the understanding and the controls to manage it. Built into the design.
Yep.
And then there's that kind of secondary question of okay, you're managing it over time within a certain range, but then if you have such a substantial change that you need to build out or add more equipment, you still have a substantial time lag to do that, correct?
Yeah, those are usually some sort of weather event. And I can describe that. Years ago, I had one of my partners was in Australia, and it was January or February. I can't really remember what month it was. And their power grids were going down because the air conditioning load was just enormous. It was really hot. At the same time, we had a polar vortex coming in here, and this was the 2014 or 16. And one of my buddies sent me a deal and says, my heat pump, the outside air was minus 16, and it was minus 30 wind chill. And he sent me a screenshot that says, my heat pump thinks it's 48 outside. Okay. Well, that was his inner water temperature. Okay. So if you have within that a very reliable forecasting of the weather, you can anticipate that and manage for it. Those big peaks in a giant water loop can simply be absorbed easily.
Right, and that connects to the comment about the potential in a large-scale system for AI or machine learning to predict and optimize for that.
Yeah, and you want to be careful, because we have machine learning, we have the artificial intelligence that's out there. Does anybody know what's coming next? It's parallel processing. Think NVIDIA. All right? All those edge devices may be, I've seen numbers anywhere from 10 to 50 times increased electrical loads from what AI has done, okay? So get prepared, okay? This thing can get wild and it can do it fast because guess what? Wall Street likes to throw money at the AI people, don't they? Yeah, they're gonna do it, all right?
One more question? Okay. Oh, great. And then anyone who wants to sign up for the credits, come on up to this table and give me your signature.
And please do that.
Hi, Alex Minity from Brightcore. My question's a bit conceptual because I've never actually seen this, and you talked about it a little bit earlier. The ambient temperature loop, separate to the bore field, right? To the typical bore field that would be installed in site.
No, just restate what you're trying to ask.
Well, my question is, what exactly is the ambient temperature
Okay,
loop?
okay.
Basically.
Okay. So you can have a district system. It can be 2 pipes, 4 pipes, whatever, okay? You know, I can have a hot water out and a return from the hot water, and I can have a chill water out and a return from the chill water, all right? Or I can have a 3-pipe system where I got chill water going out, hot water going out, and I bring them both back through a central return. But they always go to the plant, every one of them. And so I can have a 2-pipe, 3-pipe, 4-pipe system. But an ambient temperature loop is simply a loop. It's a circle. And all it has is a pump on it to move that fluid around. That's it.
And this connects to every building on the system.
Every building connects, and every heat and sink and source connects with a parallel connection, picks up fluid, right? Here's the big pipe. It picks up the fluid, goes through the building, and comes right back in, downstream. That's old technologies. There's some pumping manufacturers that developed this years ago. I have some of the original studies that was done on one-pipe systems. And I'm gonna tell you that in one of my companies, the Gray Edge, I have a pumping savant. You know Bill. Yeah, this guy's, when it comes to moving water, he can do it with the least horsepower of anybody. He's really good, okay? But he's elderly too, like me, all right? And so hopefully we can get some of this transferred to other people, okay? So yeah, all right, thank you.
Thank you.
Okay, so got a bit of a break, 15 minutes. Then I hope you're coming back here to hear about another unique individual from that part of the country, North Texas, which I know a little bit about and come back to hear Mr. Don Penn. But before that, can we have a round of applause for this unique guy? Okay. Credits up here, break, and come on back in 15 minutes.